Now there are various topics, lots of topics in this chapter. Let's see next one, which is work energy theorem. Okay, which is work energy theorem. So what does the work energy theorem say? If you do some work on a body and the the velocity of body changes, then that work done is equal to change in the kinetic energy of the body. Okay, work energy theorem says work done on a body is equal to change in kinetic energy of a body. So that is final kinetic energy minus the initial kinetic energy. So this is true when you have a constant force. This is true when you have a variable force. The work done on a body is equal to what? Change in kinetic energy of a body. Change means not initial minus final. It means final minus initial. Okay. So this is the work energy theorem. Is it clear? Okay. So then let's see problems of work energy theorem. So a body of mass 3 kg is under a constant force which causes a displacement s in meters in it, given by this relation 1 upon 3 t square, where t is in seconds. Work done by the force in 2 seconds is, tell me. Final minus initial kinetic energy. So how much would be the initial velocity? It's not given. Can I say it's 0? No. Just compare this with, okay, this kind of displacement you will have when you have a constant force. Okay, constant acceleration, because for that you have s is equal to ut plus half at square. Okay, and then you can compare this thing with this thing, so you get half a is equal to 1 by 3. Okay, compare it with this thing, half a equals to 1 by 3, that means a equals to 2 by 3. Okay, and therefore v will be equal to how much? U plus 80, but u is 0, so it is just 80, so it is 2 by 3 t. Okay, so what is work done? Work done is just half of m multiplied by v square minus u square. U is 0, so it's half m multiplied by v square only, because this is 0. So m is 3 kg and v is 2 by 3 t square, and we want work done at t equals to 2 seconds. So w at t equals to 2 seconds is equal to, this is 3 by 3, this will get cancelled, right? Okay. No. We, okay, we, yeah, we want to square the whole term. Okay, v squared. Okay, so then let's square it. So we'll have 3 by 2 multiplied by 4 by 9. This will be 4 by 9 multiplied by t square. Okay, so this thing is 4 by 2 is 2, and we'll have 3 in denominator. 2 by 3 multiplied by t square is 2 square, 4. So 4 times 2 is 8, 8 by 3. This is the answer. Okay, option D. This is simple, right? Let's see next one. Force acts on 3-gram particle, okay, in such a way that the position of particle as a function of time is given by this thing, where x is in meters and t is in seconds. The work done during the first 4 seconds is. So now x, we don't have t square, just t square in the formula. x. So what should we do? V is equal to dx by dt. We could do that in last one also, but in last one we can just compare. Okay, we have t square, so u will be equal to 0. Sorry, we have t square, so s is ut plus half at square. Comparing with that, we get u equals to 0. Okay, so here we have to find out. So it is d by dt of 3t minus 4t square plus t cube, and that is 3, and this will be minus 4 times 2t, that is 4 times 2 is 8 minus 8t, and this thing will be 3t square. Okay, derivative of this term will be 3t square. So that's your v. Okay, what is v at t equals to 0? That is u. So u is equal to 3 because t is 0. And what is v? V is this. Okay, so they are saying first 4 seconds. So let's find out v at 4 seconds. Okay, at t equals to 4. V will be equal to 3 minus 4 times 8, or 8 times 4. Yeah, 32. 3 times t square is 16. So v is equal to, this is 16 threes are 48. 48 minus 32 is, okay, 16. 16 plus 3, 19, right? Okay. Then work done will be equal to half of mv square minus u square. So it is half of 3 gram, that is 3 times 10 raised to minus 3. Okay, in kgs, and you have 19 square minus 3 square. So what is 19 square? I also don't know. Okay, so see, I do this trick. It is 361. Okay, so let's suppose you don't know some square. Okay, for an example, so I don't know 19 square. So 19 square is 19 multiplied by 19, right? Or I can say it is 19 multiplied by 20 minus 1. Okay, this thing is simple. 19 times 20 is how much? 19 twos are 38. So 380 minus 19 times 1 is 19. Okay, so yeah, it is 361, right? Okay, but it's good if you remember. So I don't have to appear for any exam. You have to. Okay, at least for now. So it is 361 minus 9. How much is this? 361 minus 9 will be 352. 352 we have divided by 2. So it is 176, right? 176 multiplied by 3. How much? 17 threes are 51, 51. Okay, this will be 530, I guess. Okay, to check. Is it correct? This is 352. 352 you have divided by, okay, divided by 2, which is 176. Right, 175 twos are 350. So this is 176. 176 multiplied by 3. So 6 threes are 18. Then you have carry 1, 5 to 8. So that's 530, right? 530 millijoules is the answer. Option D. Okay. So this is also simple. So we have questions like this. Okay. Kinetic energy acquired by a mass m in traveling distance d starting from rest under the action of a constant force is directly proportional to? Tell me, what should we do? Af minus k0 or k initial you can say is equal to what? Work done, right? And body is starting from rest. So that means initial kinetic energy is 0. So final kinetic energy is work done. And what is this force? It is a constant force. So for a constant force, kinetic energy is just force times displacement. Okay. So they are asking whether it's proportional to m raised to 0, square root of m, or 1 upon root m. Tell me what will be the answer. Does it depend on m? So it is m raised to 0, right? M raised to 0. It does not depend on m. Okay, next question. Particle of mass m at rest is acted upon by a force P for time t. Its kinetic energy after an interval t is. Tell me. It is starting at rest, okay, acted upon by a force for time t. Force is P. So P equals to final momentum you can say, okay, mv minus mu, okay, u is 0 divided by t, okay. So mv, the final momentum, equals to pt, and you just want the kinetic energy, okay. So this will be final momentum. I can say pf is the final momentum, which is equal to pt. So kinetic energy is equal to pf square upon 2m, that is mv square, that is p square t square upon 2m. So the option B. Okay, so very simple. Next one, the rate of decrease of kinetic energy is 9.6 joules per second. Find the magnitude of force acting on a particle when its speed is 3 meters per second. Okay, rate of decrease in kinetic energy. So dk by dt. So what is dk by dt? It is d by dt of half mv square. M will not change, we can say, okay. So it's half m multiplied by d by dt of v square. Okay, so how do we do this? It is d by dt of v square. Okay, so we can say it is 2v times dv by dt, right? Okay, so it is half m multiplied by 2v times dv by dt. And what is dv by dt? Acceleration. So we get this 2 gets cancelled. Mv multiplied by dv by dt, that's acceleration, that is m into a multiplied by v. So m times a is force, and you have dk by dt equals to f times v. Okay, so actually this question we should have seen afterwards. Okay, but anyways, okay, because this is the expression for power, and power is rate of change of energy. Okay, so f times v is dk by dt, and what is dk by dt? It's 9.6, and we are given with speed, v is also given, so it is f times 3. Yeah, so 9.6 upon 3, how much? 3.2. 3.2. Okay, so it is 3.2 newtons. This is the answer. Okay, but still this question is clear. Okay, but we'll just direct use this formula because rate of change of energy is power and power is given by F times V. Okay, as we'll see in this lecture or in next lecture. Okay, mostly in next lecture. So next, let us see conservation of mechanical energy, law of conservation of energy. So see, we have work done on a body equals to change in kinetic energy, okay, Kf minus Ki. And when body is acted upon by a conservative force, then we can define potential energy also. And we have work done equals to minus of change in potential energy, okay. So we have work done equals to change in kinetic energy, which is equal to minus of change in potential energy, okay. So we can equate those two, and what do we get then if we equate those two? So we get Kf minus Ki is equal to minus of Uf minus Ui, okay. And that's why rearranging the terms, we get that initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. And this is known as the law of conservation of mechanical energy. Okay, this is known as the law of conservation of mechanical energy of a body, right? So the sum of potential energy and kinetic energy remains constant. But when will it remain constant? When we can define the potential energy. And when can we define the potential energy? When the body is acted upon by conservative force only. So if there is only conservative force acting on a body, then sum of its potential energy and kinetic energy remains constant. Okay, clear? Yes, no? If there is friction, etc., there will be losses and this thing will not hold. Okay, so then as an example of this, we see vertical circular motion. So in case of vertical circular motion, see, let's suppose body is at this position. Okay, and so for an example, we have suppose a ball or a stone connected to a string and you whirl it in vertical circle. So what will happen now? It will have uh, some tension in the string acting on this point, acting at this point, okay, and there will be some gravitational force which is acting downwards. Okay, so tension is also acting towards the rigid position or okay, rigid support, and the gravitational force is also acting downwards. So what will be the centripetal force at this point? It is sum of those two, right? Let's suppose this is your hand and you are whirling that stone in vertical circle. So when stone is at this point, the string is like this, your hand is here. So tension acts towards the rigid support. Okay, tension on the stone. Okay, tension in the string acts towards the rigid support, and there will be gravitational force also. So what are the forces acting along radius and towards center? It's tension and gravitational force. And therefore I can say at this point the centripetal force is equal to what? Tension plus gravitational force. Okay, yes, no? At this point, at the bottom point, the tension is acting upwards, but gravitational force is downwards. So what is the force towards center? It is tension minus the gravitational force. Okay, so FCP at B is P minus mg, right? Then now what we can do is, let's suppose we want to find out the minimum speed with which this ball should be revolved. Okay, it should be moved from this point such that it completes the vertical circle. So it has minimum speed at this point, means the centripetal force is minimum, and centripetal force is provided by the tension and the gravitational force. So gravitational force or weight of that ball will not change. The tension will be 0. So if we put tension equals to 0, what do we get? We put tension equals to 0. What do we get? We get mv square upon r is just equal to mg because tension is 0. Okay. And therefore, we take r on this side. We get va square is equal to rg, and therefore va is equal to square root of rg at this point. Okay. So velocity in vertical circular motion, the minimum velocity at the topmost position is equal to square root of rg. Okay. Minimum velocity at topmost position is square root of rg. Then what we can do is we can apply the law of conservation of energy, and we can find out the minimum velocity at this position as well as at this position. So we do that. So minimum velocity at this position, which is midway point, you can say, okay, there it's square root of 3gr, and at this point it is square root of 5gr. Okay, so we just have to remember these formulae. So here it's square root of gr, here it's square root of 3gr. Let me use different color. V equals to square root of gr. At this point v is equal to square root of 3gr, and at this point v is equal to square root of 5gr. Okay, we have to remember these things. And then now we can find out tension in the string also. So at this point we consider tension is 0. What will be tension in the string at this point? Can you tell me? At this point, what is the centripetal force? So along radius towards center, just tension, right? Okay. So at this point, centripetal force is equal to tension, or you can say tension is centripetal force. So how much will be the tension? T is equal to, okay, centripetal force is mv square upon r. Put v equals to this value square root of 3gr. So you have m upon r multiplied by square root of 3gr square, 3gr. So r and r will get cancelled. It is m times 3g, or you can say 3mg. Okay. So at this point, the tension will be 3mg. Similarly, we can find it at this point. So here you have tension minus, right? Okay. Here you will have 6mg. Okay. All right. So we have to remember these formulae also. Okay. The tension. So now when tension at A is 0, tension here will be 3mg. Tension here will be 6mg. So now if we find the difference in tension, okay, this is true for any velocity. So tension is 0 for minimum velocity, but difference in tension is, it is valid for any velocity. What is difference in tension between these and this point and this point? It is 3mg. Okay. What is difference in tension between this point and this point? It is 6mg. Okay. So we have to remember this thing also. Is this thing clear? Okay. So difference in tension is 3mg, right? Okay. All right. And then now we can apply the law of conservation of energy to the spring block system. So what is spring block system? We have a spring like this. We connect a block to that spring, and this block can slide over this horizontal surface. So we consider this surface to be frictionless, okay, and then we find out what will be the velocity of this spring block system at each and every position, okay, then what will be its potential energy, kinetic energy, etc., etc. So now we know that the spring force is given by what? Minus kx, okay, spring force is given by minus kx. So if we pull this block by distance x, spring force will act towards the mean position, and it is minus of k into x, right? So now if we want to stretch it from some position to some other position, let's say xa to xb, we'll have to do some work, and that work done is stored as what? Increment in potential energy of the spring block system, because we are doing work against the spring force, which is a conservative force, okay. So that work done we can find like this: work done is negative of integral from xa to xb of the spring force times dx, okay, and it will come out to be k times xb square by 2 minus k times xa square by 2, and comparing this, that it will be change in potential energy, we get the formula for the potential energy of the spring, which will be half of k into x square, okay, because potential energy at b minus potential energy at a is half of k into xb square by 2, half of k into xb square minus half of k into xa square. So comparing this, we can find the formula for potential energy. It is half of k into x square, okay, that's potential energy of the spring block system. But for that, what we do is we set potential energy at x equal to 0 as 0, okay. We have to set manually potential energy at x equal to 0 equal to 0, okay, because what we can find out is just difference in potential energy and not the potential energy at a particular point. Is this point clear? Yes, no? Okay. So what we do is, for simplicity, see, now if you have x equal to a equal to 0, okay, xa equal to 0 and xb is x, then we'll get what? Xa is 0, so this term will become 0. We'll have u at x minus u at 0 will be k into x square divided by 2, or half of k into x square. So u at x minus u of 0 is equal to this thing, okay. So what we do is, for simplicity, we set this u of 0 equal to 0, potential energy at 0 equal to 0, and then we get this formula, half of k into x square. So this is for simplicity only, okay, because whatever potential energy you will have at x equal to 0, that's your reference, okay. Is it clear? Yes, no? Okay. So now suppose your spring block system, it vibrates from minus a to plus a, okay. You pull that spring or that block, spring will get stretched, you release it, then what will happen? The spring block system will vibrate, spring will vibrate, okay. Along with that, block will also move like this. So let's suppose it moves from some minus a to plus a, okay. So we can apply the law of conservation of energy. So u at x equal to 0 plus k at x equal to 0 is equal to u at a plus k at a. So now see, that block will move like this. So at extreme position, what will happen? The kinetic energy will be 0. Why will it be 0? Because it goes to extreme position, stops there and comes back. Okay, so for extreme position, what will happen? Kinetic energy will be equal to 0. Okay, so kinetic energy is 0 at x equal to a, extreme position, and for x equal to 0 we have said that u is equal to 0. Okay, and therefore we'll have some kinetic energy at x equal to 0, which will be equal to potential energy at x equal to a. So half of m into v0 square is equal to, we have half of k into a square. Okay, because x is equal to a, and comparing this we get, okay, this half and half will get cancelled out, v naught square, that is speed of this spring block system at x equal to 0 will be how much? So square of that is k upon m into a square, and therefore v naught is equal to root of k upon m a. Okay, so this is the formula. Clear? Yes, no? Okay, right? And then again substituting this thing. Okay, again substituting this thing, and taking some different x, not extreme, not mean position. Okay, taking some different x, we get v equals to speed of a particle at a particular x equal to square root of k upon m multiplied by a square minus x square. For that, what we do is, again we apply the law of conservation of energy. Okay, so we get this formula, v equals to root of k upon m multiplied by a square minus x square. Okay, so again we have to remember this formula too. Okay, so is there any question till this point? Okay. So then if we plot the potential energy and kinetic energy of the spring block system, potential energy is just half of k into x square. So its graph will look like this. Okay, its graph will look like this. And total energy is constant because this is a conservative force. So graph of total energy with respect to position looks like this. And how will you find kinetic energy? So either you can use this formula, or you can subtract potential energy from the total energy, and you will get a curve like this. So this is the curve for kinetic energy of the spring block system. Okay, any question? Okay, so now we'll see some problems based upon these things. Okay, let's see some simple problems. So what is minimum velocity with which a body of mass m must enter a vertical loop of radius r so that it can complete the loop? Tell me. Okay, so can you be sure that if it enters with this velocity, it will complete the loop? Okay, so with what velocity can you be sure? Root of high gr, because let's suppose it enters at this point. Okay, body enters at this point. So if its speed at this point is root of 5 gr, then only it will cover the complete circle, right? Okay, so if it enters at this point, see, for loop we have to consider all the points, right? So if it enters at this point with square root of gr, it will not be able to complete. Okay, so that's why the answer is square root of 5 gr, minimum velocity required at the bottom. Okay, this is simple. Let's see next one. Mass m is attached to a thin wire and whirled in a vertical circle. The wire is most likely to break when? Tell me. Option A, incline. when the mass is at lowest point, because tension is maximum at that point. Right, very good. Next one, a body initially at rest sliding along a frictionless track from height h as shown just completes a vertical circle of diameter AB equals to D. The height h is equal to. Tell me, what should we do? Means out of 7 GR. Why? Okay. So actually, this problem can be solved using law of conservation of energy. Okay. Or, okay, let me explain with law of conservation of energy first. So I can say potential energy at C is equal to kinetic energy at A. Okay, potential energy at C equals to kinetic energy at A, because there is no kinetic energy here and potential energy is 0 here, height is 0. Okay, so you can say mgh is equal to half of m into v square. And how much is v square? Root 5 gr square. So gets cancelled, so you have 2gh is equal to, okay, root 5 gr square, that is 5 gr. Gg gets cancelled, so you have h is equal to 5 by 2 r. Okay, they are asking in terms of diameter. R is equal to diameter upon 2, right? So it is 5 by 4d. This is the answer. Okay, so here you have applied the law of conservation of energy. Then it can be solved like this. If you release an object from height h, how much velocity does it attain? Right, v equals to root of 2gh. And how much velocity do you want at this point? Square root of 5 gr. So root of 5 gr is root of 2gh. Okay, root cancelled, gg cancelled. So you have h equals to 5 by 2 r. Okay, you can solve it faster using this method, right? Okay, not a trick, you just have to remember what will be its velocity at this point. Okay, so this is smart way of solving this. Anyway, this way will also not take any time. Within few seconds you will solve it. Okay, so this is a simple problem. Let's see next one. As shown in the figure, a mass is performing vertical circular motion. The average velocity of particle is increased, then at which point will the string break? Most likely to break. It's point B, right? That is repeated question. Next one. Child is sitting on a swing. Its minimum and maximum heights from the ground are 0.275 meter and 2 meter respectively. Maximum speed will be. Tell me. Boy is swinging on a swing. So let's suppose there is a boy swinging on a swing. Okay. So swing goes here, swing goes here. Right. So at this point and this point, velocity will be 0. At this point, it will be maximum. Right. Because when it goes at this point, again it has to come back, so velocity will become 0 momentarily. So at this point it is maximum, v is maximum. So what changes? Let's suppose this is A, this is B. Potential energy changes, right? Okay. So we can say half of m into vb square is equal to mg h at A minus h at B. Okay, I wrote directly. This is change in kinetic energy is equal to what? Change in potential energy. Okay. So gets cancelled and you have vb square equals to 2 times g multiplied by ha minus hb. Let's put the values. So 2 times 10 multiplied by HA is 2, 2 minus 0.75. So that is 1.2, right? 1.25. So this will be 2.5 times 10, 25. So V square is 25. So V is 5 meters per second. Right, option B. Okay. Next question. A stone is tied to a string of length L and is whirled in a vertical circle with other end of the string at the center. Okay. At a certain instant of time, the stone is at its lowest position and has speed u. The magnitude of change in velocity as it reaches position where the string is horizontal. Okay. G is acceleration due to gravity is. So how much will be change in velocity when what happens? The string becomes horizontal. This is given. So you have u, okay, which is here at this point. This is u, and when string becomes horizontal, you have v. Okay, v will be directed like this. Okay, what will happen? Will the speed increase or decrease? Decrease. Okay, and how much will it decrease? You can say u equals to, so this much distance is r. Okay, height difference is r. So I can say u square is equal to v square plus 2gr, right? Okay, so we can find out v. Okay, after that, see, then we want the change in velocity, magnitude of change in velocity. So velocity at this point is in this direction, at this point is in this direction. Okay, so now you want change in velocity, that means you want u minus v, u bar minus v bar. So for that, draw u bar, which is directed like this, v bar is directed like this, minus v bar will be directed opposite to that, like this. This is minus v bar. Okay, what will be u bar minus v bar? It's addition of these two, so it will be directed like this. But in magnitude, I can say this is suppose r, which is u bar minus v bar. In magnitude, it will be u square plus v square. Okay, I want just magnitude because magnitude of change in velocity. So in magnitude, it will be u square plus v square only. So magnitude of r bar is just u square plus v square. Okay. And all the options, sorry, it will be square root of that. not u square plus v square, square root of that. Okay, and all the options are in terms of u or gl. Okay, that means we have to substitute for v. So what will be v? Take that 2gr on other side, will be u square minus 2gr. So you have magnitude of r bar or magnitude of u bar minus v bar equals to square root of u square minus v square, sorry, u square plus v square. So that is v square is, take this 2gr on other side, so it is u square not plus minus 2gr. So this will be 2u square minus 2gr, 2u square minus 2gr. This is the answer. But you can take 2 common. So it will be u square minus gr. Okay. So it is option A. You can take r equals to L, length of the string. Okay. So this is simple. Not as simple as previous problems, but this will take little bit of time, 1 to, I can say, more than 1 minute. Okay. All right. Let's move on to the next problem. Okay. Two springs A and B having spring constant Ka and Kb. These are the ratios. K equals to 2 Kb are stretched by applying a force of equal magnitude. If energy stored in spring A is Ea, then energy stored in B will be. Okay. What is given? Force of equal magnitude. Okay. So what is spring force in magnitude? Kx. And what do we want to compare? Energies. What is energy? It is half of kx square. So we have k, we have x. We don't have f in this formula, which is right. So it will be half of k square x square upon k. We can say, okay, I'm multiplying and dividing by k. So that is half of x f square divided by k. And what is equal? F is equal. So therefore I can say 2k into E is equal, right? I will move this on other side. So F square equals 2ke. This is what I get. So this is equal, Fa equals to Fb. That means Ka into Ea is equal to Kb Eb. And I want energy of B in terms of energy of A. So I will take Kb on this side. So Eb equals to, okay, Ka upon Kb multiplied by Ea. Okay, so what's that? K upon Kb is 2 because Ka equals to 2 Kb. So it is 2 times Ea. Okay, this is simple. Okay, good. Next one, when a long spring is stretched by 2 centimeter, its potential energy is U. If the spring is stretched by 10 centimeter, the potential energy stored in it will be. Tell me. Right. Very good. So U is equal to half of k into x square. I'm just explaining this for the students who will watch it later. Okay. So x1 is equal to 2 and x2 is equal to 10. Okay. So x2 is equal to 2 times x1. So therefore u2 will be equal to, because it is directly proportional to x square. Okay. So sorry, x2 is equal to 5 times x1. So it will be 5 square times u1 because it is directly proportional to x square. So it is 25 times u1. So this is the answer, option D. All right. Next one, a mass of 0.5 kg moving with a speed of 1.5 meters per second on a horizontal smooth surface collides with a nearly weightless spring of k equals to 50 Newton per meter. The maximum compression of the spring would be. Tell me what will happen. Very good. Right. So half of mv square, the kinetic energy of this ball when it collides with spring will get converted to potential energy of the spring. Okay. So kinetic energy of ball equals to P of spring. Half of m into v square equals to half of k into x square. Half gets cancelled, and we have the maximum compression x square equals to mv square upon k, m by k v square, and therefore uh, m is how much? 0.5 divided by 50 multiplied by 1.5. Okay, this thing will be 1 upon 100, right? 0.5 upon 50 is 1 upon 100, and 1.5 square is how much? 2.25, right? Okay. So this is x square. We want x actually. Let's take x equal to 1.5 divided by 10, right? So that is 0.15 meters. This is the answer. Option A. This is simple. Okay, next one. This is kind of repeated. The potential energy of a long spring when stretched by 2 centimeter is U. If the spring is stretched by 8 centimeter, the potential energy stored in it is. So x2 is, right. So x2 is 4 times x1. Therefore u2 is, because it is directly proportional to x square, 16 times u1. Okay. Next one, a vertical spring with force constant K is fixed on a table. Ball of mass M at height h above the free upper end of the spring falls vertically on the spring so that the spring is compressed by distance d. The net work done in the process is. Tell me. So vertical spring is fixed on a table. You have vertical spring like this fixed on a table, and a ball of mass M at height h above the free upper end, above the free upper end. So from upper end, the ball is dropped from height h. Ball is dropped from here, from this height. So the net work done in the process is. Tell me. So now spring has some potential energy. Okay, ball has some potential energy, right? So there will be some initial potential energy and there will be some final potential energy, and work done is equal to minus of change in potential energy. Okay, suppose ball falls till here, how much is change in potential energy? Hmm. It will be minus of mgh because it is decreasing. Okay, right, it will be minus of mgh. Then the spring will get compressed. So spring gets compressed by d. How much will be change in potential energy for the ball only? For the ball only. No, no, for the ball only. again it falls by distance d, right? So it will be minus of mgh plus d. Okay, so it is minus of mgh plus d for the ball. For the spring, initially 0, initially 0, right? Then final is minus half kd square, right? So initial minus final is minus of half of kd square. Okay, so therefore, sorry, this one was negative, this one is positive. Okay, right, because this one is falling, its potential energy will decrease, and here you have compression or expansion, potential energy will increase only. Okay, so therefore you will have minus minus becomes plus mg h plus d and minus half kd square. This is the answer. It's option A. Got it? Yes, no? Okay. So there will be this kind of problems, right? Uh, okay. So I think you can solve. Okay. We'll stop here.